So section 4.6 is on applied optimization. Applied optimization is really just looking for extreme values in the context of some formula. Of course, this formula is just modeling some situation. For example, here's a few questions to motivate what we're thinking about. What are the dimensions of a rectangle with a fixed perimeter having maximum area? Again, we're dealing with some rectangular figure, and we're looking for its extreme value, namely the maximum. What are the dimensions of the least expensive cylindrical can of a given volume? And how many items should be produced for a profitable production run? Of course, all of these questions are simply restatements of questions that ask for the extreme value of some given function. In order to solve these problems, it really is just a 5-step process. We want to first just make sure we know what we're talking about before you do any sort of understanding of what the computation. Just read the problem. Of course, take a moment to understand what's given and label unknown quantities. Make sure you understand what you're looking for. Model it and draw a picture. So in the case of the rectangle, draw some sort of rectangle and use that to introduce your variables. Number 4 is probably the hardest part, where we have to actually get an equation for the unknown quantity. It would be great if we could do it in a single variable, but if we can't, we can go ahead and use 2 equations, and that'll allow us to find or work with 2 unknowns. And finally, we're looking for extreme values, so take the derivative to find the critical points, and of course, modeling real-life situations will have some sort of beginning and end. The domain is really not negative infinity to infinity in most cases. For example, your box or your rectangular area can't be negative, so there's some bound on the end. So let's go ahead and look at this example here below. All right, so what perimeter what is the smallest perimeter possible for a rectangle whose area is 16 inches square, and what are its dimensions? All right, so I'm going to be dealing with, again, this rectangular object. So let's go ahead and start by now drawing the picture. So if we have some rectangular object, I drew it as a square, probably shouldn't have, and because we're not assuming it's a square, but we know its area is 16. And let's introduce some variables. Well, the area is equal to 16. We know that. Let's just go ahead and say its length and its height is x and y. And of course, this is what we're looking for because we are looking for the perimeter. So we're going to need x and y, and therefore we're going to need the perimeter. And again, we're looking for the smallest perimeter. So maybe we can just say, add a little bit more and say just the minimum perimeter. Now, let's get some formulas. Well, we know area is equal to x times y, and because we're dealing with 2 unknowns, x and y, we will need a second. So if you think about the area of a rectangle or any sort of quadrilateral, the sum of its widths and the sum of its heights is going to give you the perimeter. So now we arrive to 4. We have our equations, and what we need to go ahead and do is get the maximum and minimum value for x and y. What we're going to go ahead and do is just start with, what we're given. We're given that the area is equal to 16, aka x times y is equal to 16, aka that x is equal to, let's go ahead and actually, instead of solving this for x, let's solve it for y. It's just a little easier to work with x when we make a substitution. So y is equal to 16 over x. So now what I'm going to do is use this and substitute it in for the perimeter equation. So our perimeter equation, as currently stated, is the sum of 2x and 2y. And now we know y is equal to 16 over x. So the perimeter is equal to 2x plus 2 times 16 over x. And simplifying this is 2x plus 32 x to the minus 1. Now, let's go ahead and find the extreme values for the perimeter equation. Taking the derivative, perimeter prime, or the derivative of the perimeter, is equal to 2 minus 32 over x squared. And now, to find the critical points, set this equal to 0. So, let's go over and set this equal to 0. So we would have 2 minus 32 for x squared. Let's subtract the fraction from both sides, and we get 2 is equal to 32 over x squared. Multiply both sides by x squared and divide by 2. So we're going to get x squared is equal to 16. So we find x is equal to plus or minus 4. Of course, we just want the positive value here. So let's just back that up. We just want the positive value 4 because, of course, x is a dimension. It doesn't make sense to have a negative length. Now, we can go ahead and use this as our critical point and just use our first derivative test. So our first derivative test would just say, okay, we need to look not from negative infinity. This is one of those we want to go ahead and consider the endpoint 0 to 4, and then from 4 to infinity. Because again, if you were, this again is our domain on x, and you can't have negative x values when talking about area. So let's go ahead and just assume p prime is, well, we have it as a function of x, so we don't need to assume that. We have that right here. So p prime of, let's say, 1. If we plug in 1, we'll get a 2 minus 32, which is clearly negative. And let's consider p prime of 5. And of course, if you do plug in 5, you're going to get 2 minus 32 over 25, which is less than 2. So this is going to be positive. So we decrease to increase. It would make sense that this is going to give us our smallest perimeter when x is equal to 4, because we switch from decreasing to increasing. Now, to find the actual y value, remember we need to get the actual possible smallest perimeter. We just have found where that would occur with the x. So let's go ahead and just do some substitution. So again, well, actually, we don't even need to do substitution because we already have the perimeter as a function of x right here. So p at 4 is equal to, or the perimeter at x equals 4 is going to be 2 times 4 plus 32 over 4 squared, which is 16. So let's see. Oh, not 6, not that. Let's just back that up. We're not gonna square because this is just the minus 1. So it's 32 over 4. So it's going to be 8 plus 32 divided by 4 is also 8, which is equal to 16. So we have our perimeter of 4. X is 4, which means, oh, and you can really check this and verify it pretty quickly. Y is 4. So while I shouldn't have really drawn it as a square earlier, our rectangular shape with the smallest perimeter with area of 16 is when all sides are of length 4, aka it is a square. So in example 2, we are going to be working with an open top box. It is to be made by cutting small congruent squares from the corners of a 12 by 12 inch sheet of tin and then bending the sides upwards. And of course, we can draw a picture for this. So here's our 12 by 12 inch sheet of tin. And the congruent squares that we're going to be bending up are modeled in 2 dimensions like this, 3 dimensions in this picture down below. And of course, what we're trying to do is to find how large the squares should be cut from the corners to make the box hold as much as possible. So we have a box, it needs to hold something. What we're really talking about is volume. Volume for a rectangular prism is length times width times height. So where do we get the length, width, and height? Well, of course, we can model this in terms of just x. We need to cut a x by x square from the corners. So if we go ahead and look at this 3-dimensional, well, we can just realize, or we can even do it in 2 dimensions if we want, the whole length is 12, and we have to cut out 2 pieces of the x, or 2 x's. Now we also have so let's just call this our length. Let's think then you would do the same thing for the width. Both the length and the width are 12 minus 2x. The height, of course, is just the bending upwards, so that's going to be x. Now let's substitute these into our volume equation. We find V is equal to length, which is 12 minus 2x, width, also 12 minus 2x, height, just x. Now we need the critical points. We can just go ahead and do the product rule twice, or we can distribute. I'm going to go ahead and distribute. So we find volume is equal to 144 minus 24x minus 24x plus 4x squared, and we have an x off to the side still. Combining like terms, reordering, and distributing the x, we find that our volume is equal to 4x cubed minus 48x squared and plus 144x. This is V. Critical points, to maximize, we need the V prime, or the derivative of the volume. So V prime is equal to 12x squared minus 96x plus 144. Setting equal to 0, we can go ahead and solve this by factoring out a 12. So that would give me a 12, and then we would have x squared minus 8x plus 144 divided by 12 is 12, equal to 0. So we find 12, and then x minus 2, and then x minus 6 is equal to 0. So we find our critical points of 2 and 6. Now, let's go ahead and actually see if this is a maximum. So and we have 2 critical points, so let's consider what to do with that. Just like before, we should go from 0 to 2 because we can't have a height that is less than 0. And then we can go from 2 to 6, the domain from 2 to 6, just we'll need to test the value in there. And you may think, well, what about 6 to infinity? Do I need that? Well, let's be careful because, again, this is the domain on x. If you plug some value greater than 7 or greater than 6 into this, notice it'll make it negative. So we don't need to even concern ourselves with this last piece of the domain. It just doesn't make sense in terms of a box. So plug this into V prime of x. So I would encourage you to just go ahead and use this factored form of V prime. Just makes it a little easier to just test. For example, say 1. When you plug in 1, you get positive 12, negative 2, and then you would have a negative 6. So that is going to be positive, so increasing, which is looking good for a maximum. And then V prime of, say, 3. When you plug that in, you'd have positive 12, and then 3 minus 2 is positive 1, and then 3 minus 6 is negative, so that is going to be equal to negative, which is decreasing. Awesome. That is a maximum. So what we have is a max x at, or I guess when, let's try that again. We have a maximum volume if x is equal to 2. Now remember that we wanted to know how large should the squares be cut from the corners to make the box hold as much as possible. So we've answered that. We have x is equal to 2, so it should be cut 2 inches away. And if we slide down a little bit more, we'll have the graph right here. And you can see if we just model this with our function that we had described right here, y, or v in our case, is equal to x times 12 minus x, or 2x, and then times itself is squared, and there's the domain that we talked about. To find that actual maximum value, we would just have to go ahead and plug it back into the original volume equation. So while not necessary, let's go ahead and just do that for to make sure our answer makes sense. So if I were to plug it back in, v at 2 is equal to the function over here on the right, or the one above, is just going to be 2. And then we have 12 minus 4 squared. So in other words, what we're looking at is 2 times 64, or 128 inches cubed for volume. In example 3, you have been asked to design a 1-liter can shaped like a right circular cylinder. Go for you. What dimensions will use the least amount of material? So let's go ahead and, we don't have a picture given this to us this time, so let's just see if we can illustrate this a little bit. So if we're thinking about a can, it's going to have a circular base. It's going to go up, we're going to have the walls, and then we'll have a top. So I am not the greatest artist, but it does just give me some sort of figure that I can look at. Now, let's go ahead and get our formulas and see what we're given. Now, we're looking to find the dimensions that use the least material, and we know that it is simply going to be 1 liter. And of course, a little mistake here, a liter is a measure of volume, not a measure of area. So our volume, well, let's see what we know about that. If you think about a circle, pi r squared, and then when you add a dimension to it, it is equal to h. We also know that our volume is equal to 1,000 centimeters cubed. If we want to find or maximize the actual design or the material used, we're going to have to actually maximize the area of the can. Actually, not maximize, we want to use the least, so we want to minimize the area of the can. So let's get the area. Well, the area of a can is simply going to be 2 circles plus the actual wall. So the 2 circles, no problem with that. That is simply going to be 2 pi r squared. Pi r squared is every circle, and we have 2 of them. Now, if you're thinking about the actual wall, we're going to be going up, and we're going to be going up the circumference. So 2 pi r is the circumference multiplied by h, and we actually have the third dimension, the height, to it. So if we're looking at this, we have 2 variables, but we also have some information given to us. So let's go ahead and use this information up here to go ahead and get our area formula in terms of just 1 variable. So let's just solve volume, which is in this case 1,000 or 1 liter, is equal to pi r squared h. Let's go ahead and solve this for h, and then we can substitute h back in. So in other words, h is equal to 1,000. So I guess we're solving this for h. So h is equal to 1,000 divided by pi r squared. Now, substitute this back in. We find that the area is equal to, let me go ahead and match the colors just to make it flow a little bit better. That the area is equal to 2 pi r squared, no h there, and then we have plus 2 pi r times h. So 1,000 divided by pi r squared. Let's clean this up a little bit. Nothing much we can do with the first one, so that's just going to be 2 pi r squared. And let's see, we have a cancellation of the pi's. We have a cancellation of the r on top with one of them on the bottom. So we have plus 2,000, 2 times 1,000, divided by r, or let's just go ahead, and since we're taking the derivative, r to the minus 1. So this is our area. To maximize, or minimize, sorry, we need to go ahead and find the critical points. So let's do that. That is to say, a prime, and yeah, I'll do this right here. A prime is equal to 4 pi r, and then we have minus 2,000 over r squared, and we're going to set this equal to 0. Solve this one very much like before. Just simply add the 2,000 over r squared to both sides. So we have 4r is equal to 2,000 over r squared. Multiply both sides by r squared, and we have 4 pi r cubed is equal to 2,000. Divide this by 4 pi. So I'm going to work this over here. So we have the dividing by 4 pi, we have r cubed is equal to 500 over pi, and taking the cubed root, you find r is equal to the cubed root of 500 over pi. Approximately, this works out to 5.42 centimeters. 5.42 centimeters. Now, again, we can go ahead and do the first derivative test for Extrema, and that would work out just fine. We can also go ahead and use the second derivative test for Extrema. So just to remind you what that is, we just have to go ahead and find one more derivative. So 4 pi, and then we would have a plus, I'm just taking the derivative of this right here, would have the 2, which would come down in front to give you 4,000 over r cubed. Now, if you go ahead and take the critical point right there and plug it in, if you were to take a double prime of 5.42, you would find that that value is actually going to be positive. If that is positive, well, think about what that means. That means we're simply concaving up, which implies that we have a shape like this, which implies that we have a local minimum, which was exactly what we wanted. And we can see this graphically down below. So we have short and wide, or tall and thin, and you can see right here on the right, we have our critical point, and we verified using the second derivative test for Extrema that that is indeed our minimum value. So if we remember our initial question, it asks what were the dimensions. What we have found is the actual minimal area. So how do we go from here to get the actual dimensions? So what we're going to need to do to find the actual dimensions, we know that h, let's get to the right pen, okay, there we go. We know that h we had found to be 1,000 divided by pi r squared by just rearranging our volume formula. And when we plug in, all right, let's back up. What do we have? We found r. We had found the minimum value wherever r occurred. So right there. So we can take that value and plug it in. Do a little bit of simplification. So h is equal to 1,000 divided by pi, 5.42 squared, and just plug that into a calculator or crunch those numbers, you'd find is 10.84 centimeters. So we have now found the two dimensions. That is to say the height is equal to 10.84 centimeters and the radius is equal to 5.42 centimeters.